Hey everyone, welcome back. So in all of our previous videos and examples of solving our larger 3x3 linear systems, we've just talked about the mechanics and processes for actually doing the algebra and solving our systems. In this example, we're going to actually set the system up and solve it. So we're looking at an application or a word problem here. And in this problem, we are told that a company sells their product in bundles of 2, 4, and 10 for prices of $2, $3, and $5 respectively. We're also told that a store sold a total of 50 of these bundles and 192 products in total for $142. So our task is to figure out how many of each bundle type were sold at this store. So in order to do this, we're going to have to set up and solve a system of 3 equations and 3 unknowns. And so before we start writing any equations down, let's go ahead and define our variables. And so our variables are going to be these unknown quantities that we are trying to figure out, and that's how many of each bundle type were sold. So we can go ahead and let X represent the number of the first bundle sold, Y can represent the number of the second bundle type sold, and Z can represent the number of the third bundle type sold. So now that we've identified our unknowns and defined our variables as these number of bundle types sold, right? So bundle 1, is the bundle of 2 products for $2. Bundle 2 is the bundle of 4 products for $3, and bundle 3 is the bundle of 10 products for $5. So with that and the rest of the information involved, we can start writing down our system of equations. So one of the pieces of information we are told is that the total number of bundles sold is 50. So if we add up all the number of bundles sold, we have to get 50. Well, X, Y, and Z are representing the number of each type of bundle being sold. So if we take X, add it to Y, and add it to Z, we should end up with the total numbers of bundles sold, and that is 50. So our first equation here is X plus Y plus Z is equal to 50. Another piece of information that we are given that we haven't used yet, but we should be able to work with, is that in total, 192 products were sold at the store. And so these products are coming from all these different bundles, right? The first bundle type contains 2 products per bundle. The second bundle type contains 4 products per bundle. And the third bundle type contains 10 products per bundle. So our second equation is just going to be describing the total number of products being sold from all the different bundle combinations. How many products does the first bundle type contribute? Well, it's going to be 2 products per those first bundle types, and there's X of those first bundle types. The next piece of our second equation, that term we have to add in, is going to have to take into account the number of products that are coming from the number 2 bundle type being sold. Well, we're going to sell Y of these number 2 bundles, and each of those number 2 bundles contains 4 products. So 4Y will count how many products are coming from or were sold by the second bundle type. And similarly, for the third bundle type, we know that there are 10 products per bundle and there are Z bundles. So 10Z is going to be how many products are coming from that type 3 bundle. And if we add 2X, 4Y, and 10Z together, we're going to get the total number of products within all these bundles that were sold, and that is 192. So that is the second equation in our system. Right, so we need one more equation to finish setting our system up, then we can go ahead and start solving it. And that last equation is going to have to take into account that all this merchandise was sold for $142. Well, we know the first bundle type costs $2 per bundle, so that'll be another 2x for that first term of our third equation. The second bundle type is going to be at $3 per bundle, and there are Y of those bundles. So 3Y takes into account or counts how much money was generated by selling these type 2 bundles, $3 per bundle. And then the last term is going to be the amount of money coming from the third bundle type. Those were $5 each, and we're selling Z of them. So the total money from those is going to be 5Z. And so if we add up all the money, we have to add up to 142. And so this gives us our 3x3 system of linear equations. Now we just have to solve it for X, Y, and Z. And so if we're going to solve this system of equations, we have to decide which variable we want to eliminate. I think I would go ahead and eliminate X here, but in all the cases, it doesn't really matter. Just make a choice and go with it. And so one way to eliminate x from a pair of these equations is just taking equation 2 and subtracting equation 3 from it. So 2x minus 2x eliminates those x's. That's what we were hoping to do. 4y minus 3y leaves us with a single y. 10z minus 5z leaves us with 5z. And that's going to be equal to the difference between 192 and 142. And that's equal to 50. So this is going to be our fourth equation, or our first equation in our reduced 2x2 system. Y plus 5z is equal to 50. All right, and so now we need to eliminate x from another pair of our original three equations. Let's go ahead and do it using equations 1 and 2. If we take equation 2 and subtract away from it 2 times equation 1, that should also eliminate x. So I'm not going to write out all the multiples of the equations like I usually do. Let's try to speed it up a little bit here. So we're not doing anything to equation 2, but we're subtracting 2 times equation 1 from equation 2. So that'll be 2x minus 2 times this x value, eliminating the x's. Then we have 4y minus 2 times this y value. So that'll be 4y minus 2y, leaves us with 2y. Next up, we have 10z minus 2 times this value, so 2 times z. 10z minus 2z leaves us 8z. And then on the right-hand side, we have the constant from equation 2 minus 2 times the constant from equation 1. That's going to simplify to 192 minus 100, or just 92. Now we're in an excellent spot to be in because we've successfully reduced our 3x3 system involving x, y, and z to this simpler 2x2 system involving just y and z. And so now we can solve it pretty quickly for y and z, and then back substitute to find x. Again, there are always various routes we can take to solve our systems of equations, right? The substitution method looks pretty tempting here. I'm going to go ahead and stick with our elimination method. I noticed that if I take 2 copies of equation 4 or multiply equation 4 by 2 and then subtract equation 5 from it, that'll eliminate the variable of y, allowing us to solve for z. So let's go ahead and perform these steps. So we're multiplying equation 4 by 2. That'll turn this into a 2y, a 10z, and a 100. So this 2 times equation 4 minus equation 5 is going to look like 2y minus 2y. That gives us 0 y's. Then we have 10z minus 8z. That'll leave us with 2z. And that's going to be equal to 100 minus 92, which is 8. So after dividing both sides by 2, we see that z must be equal to 4. And now that we know that z has to be equal to 4, we can start back substituting to find y and x. Next, we'll go ahead and find y using equation 4. We know y plus 5 times our z value of 4 is equal to 50. So y plus 20 is equal to 50. That tells us y has to be equal to 30. And now we just need to find x. And well, our first equation is probably the best one to use to help us find x. It tells us x plus y plus z is equal to 50, or x plus 30 plus 4 is equal to 50. Well, 50 minus 34 is 16, and that must be our x value. And so our final answer for this application problem, expressed as an order triple, is x, y, z is equal to 16, 30, and 4. Interpreting that in the context of our problem, we were trying to figure out how many of each bundle type were sold. Well, we know we'd have to sell 16 of the first bundle type, where it contains 2 products for $2 per bundle. We have to sell 30 of the second bundle types, where we have 4 products per bundle, and each bundle costs $3. And then to finish it off, they must have sold 4 of the third bundle types, where that contains 10 products, and each bundle is $5. The applications of these linear systems of equations really are limitless, and they only really get more interesting the larger these systems become.